Gazing up at the night sky, have you ever wondered if the stars hold mirrors to our own world? Not just distant cousins in the vast cosmic ocean, but planets that feel like eerie time capsules, snapshots of Earth's own turbulent past frozen in time. Picture a world where glaciers stretch as far as the eye can see, locking the entire surface in an eternal ice age, or a planet so violently volcanic, its landscapes churn with molten rivers, just like Earth during its fiery infancy. These aren't scenes from science fiction, they're real places scattered across the galaxy, each one a bizarre reflection of a chapter from our planet's own story. What if I told you that by studying these distant worlds, we're not just exploring the universe, we're unraveling the secrets of our own home? Every crater, every storm, every whisper of an atmosphere on these alien worlds holds clues to the forces that shaped Earth over billions of years. Think of it as cosmic archaeology, where instead of digging through layers of rock, we peer through telescopes to find planets trapped in time. Some resemble Earth during its most extreme transformations, periods of global freezing, suffocating greenhouse climates, or even the chaotic aftermath of colossal asteroid impacts. Others feel like glimpses into a future Earth might one day face. This journey isn't just about scientific curiosity, it's about connection. These distant worlds remind us that Earth's story is written in the stars, part of a grander tapestry of planetary evolution. And as we uncover each one, we're piecing together a puzzle that stretches across space and time. So buckle up, we're about to visit 20 of the most astonishing planets ever discovered, each one a mirror to Earth's past in ways that will leave you awestruck. From frozen relics of ancient ice ages to worlds drowning in primordial oceans, prepare to see our planet's history reflected in the most unexpected corners of the cosmos. The universe, it turns out, has been keeping a scrapbook of Earth's life, and we're finally turning the pages. Our first stop takes us to a world so cold, its very existence feels like defiance. Imagine a planet where winter never ends, not for centuries, not for millennia, but for millions of years. This is the Ice Age twin, a frozen mirror reflecting Earth's most brutal glacial periods. Its surface is a labyrinth of glaciers so vast they could swallow continents whole, their icy fingers creeping across valleys and mountains with slow, relentless patience. Scientists think this world's deep freeze comes from a delicate dance, an orbit so precise it locks the planet in eternal twilight, with only faint starlight to warm its frozen crust. But here's the spine-tingling part. Earth once looked eerily similar. Rewind 700 million years, and our own planet might have been a snowball Earth, a global icehouse where even the equator froze solid. Yet life clung on, hiding in cracks under ice or near volcanic vents. That's why the Ice Age twin captivates researchers. Beneath its frozen shell, they've detected signs of subsurface ocean's liquid water trapped between ice and rock, warmed by the planet's own internal heat. It's a haunting parallel to Earth's ancient survival stories, where microbes thrived in the most hostile corners. Could this distant world harbor its own hidden biosphere? The possibility sends shivers down scientists' spines. If life exists there, it wouldn't be green forests or crawling creatures. It'd be something far stranger, adapted to darkness and cold, a testament to resilience written in ice. Every scan of this planet isn't just about uncovering alien life. It's about decoding Earth's own frozen past, a time when our planet teetered on the edge of oblivion and somehow endured. From the frozen stillness of our Ice Age twin, we now plunge into a world of fire and fury, the volcanic Prodigy, a planet that wears its youth like a badge of chaos. This isn't just a world with volcanoes, it's a world built by them where eruptions paint the sky in perpetual twilight and rivers of molten rock carve continents in real time. If you could stand on its surface, though no probe or spacesuit could survive long enough, you'd witness a spectacle Earth hasn't seen for billions of years. A newborn planet still stitching itself together, one explosive burst at a time. What makes this world so extraordinary isn't just its violence, but its familiarity. Scientists believe this is almost a perfect mirror of Earth during the Hadean Eon, when our own planet was a seething cauldron of magma oceans and asteroid impacts. Back then, Earth's crust was thin and brittle, fracturing under the pressure of the molten fury beneath, a process we can now watch unfold in real time on the volcanic Prodigy. Its surface is a patchwork of lava lakes and collapsing landmasses, where new crust forms and shatters in cycles that last mere decades instead of millennia. The most tantalizing clue: this planet might be caught in the act of developing tectonic plates, the very geological machinery that shaped Earth's mountains, oceans, and even the conditions for life. Some researchers think they've spotted slabs of crust diving beneath others, like the first whispers of subduction zones. If confirmed, it would be like stumbling upon a cosmic time lapse of Earth's own geological awakening. But here's the twist: while Earth's volcanic phase eventually calmed, allowing oceans and atmospheres to stabilize, the volcanic Prodigy shows no signs of slowing down. Its star bathes it in relentless radiation, stirring its molten interior like a pot on a stove. That's why astronomers call it a laboratory for planetary puberty, a place where we can study the growing pains every rocky world might endure. And hidden in its chaos could be answers to one of Earth's oldest mysteries: how, amid all that fury, our planet found the balance to cradle life. Leaving behind the fire and fury of our volcanic world, we now descend into something far more sinister, a planet where oceans don't cradle life but dissolve it. Welcome to the acidic mirror, a world drowning in seas so corrosive they'd eat through metal in seconds. These aren't gentle waves lapping at sandy shores. They're churning, toxic soups of sulfuric acid and other caustic chemicals, bubbling under a hazy, orange sky. At first glance, it seems like a dead world, a place where nothing could possibly survive. But that's where the mystery deepens, because this nightmare landscape might hold the very secrets to how life first sparked on Earth. Rewind 4 billion years, and our own planet might have looked startlingly similar. Before blue oceans and green continents, Earth's early seas were likely a blistering mix of acids and toxic compounds, a byproduct of constant volcanic outgassing and asteroid bombardments. Yet somehow, against all odds in those hostile waters, the first fragile molecules of life began to stitch themselves together. That's why the acidic mirror fascinates scientists. It's like looking into a cosmic petri dish, a snapshot of Earth's most inhospitable era frozen in time. Recent scans have detected something unexpected beneath the planet's acidic surface: complex organic molecules, the building blocks of life, swirling in those deadly tides. Even more intriguing, some of these molecules arrange themselves into structures that resemble primitive cell membranes. It's not life, not yet, but it's a tantalizing hint that even in the most brutal environments, the universe keeps trying to assemble the puzzle pieces. The real question isn't just whether life could emerge here, but how. Could the very acidity that seems so hostile actually act as a catalyst, speeding up chemical reactions that lead to complexity? Some researchers think so. They point to Earth's own extremophiles microbes thriving in acidic hot springs or deep sea vents, as proof that life doesn't just endure harsh conditions, it can exploit them. If that's true, then the acidic mirror isn't a dead end. It's a workshop, a place where the rules of life's origins are being rewritten in real time. And here's the haunting thought: if life did arise here, it wouldn't look like anything we recognize. No fish, no algae, nothing that fits our Earth-centric definitions. It'd be something entirely alien, forged in acid instead of water, a testament to life's stubborn versatility. That's the true gift of this world. It forces us to rethink not just our past, but the very boundaries of what life could be. Every drop of its toxic oceans is a challenge, a dare from the universe. You think you know how life begins? Look again. Stepping onto the oxygen desert would feel like standing at the edge of space without a suit, a world where every breath is a struggle and the sky offers no comfort. This planet's atmosphere is so thin, it makes the summit of Mount Everest seem like a tropical paradise by comparison. The air here isn't just lacking oxygen, it's barely there at all, a wispy veil of nitrogen and trace gases that cling to the surface like a fading memory. Yet this desolate place holds a mirror to Earth's own adolescence, a time when our atmosphere was just as inhospitable, long before green things learned to harness sunlight and fill the skies with breathable air. What makes this world so chillingly fascinating isn't just its emptiness, but what that emptiness represents: a cosmic pause button pressed on a critical moment in planetary evolution. Billions of years ago, Earth's air was a toxic cocktail of methane, ammonia, and carbon dioxide, with almost no free oxygen. Then came cyanobacteria, tiny organisms that invented photosynthesis and slowly, stubbornly, transformed the entire planet. The oxygen desert is like a snapshot of Earth before that revolution, frozen in time. But here's where the story twists. Scans of this planet's surface reveal something unexpected: ancient riverbeds, dry lake basins, even minerals that only form in the presence of liquid water. This world wasn't always a barren wasteland. Once it might have had lakes, maybe even seas. So what happened? The leading theory is as unsettling as it is enlightening. Unlike Earth, where life reshaped the atmosphere, this planet's chemistry might have stalled, trapped in a geological equilibrium that never allowed the leap to oxygen. Without that critical shift, its water vanished, its skies thinned, and its chances for complex life evaporated. That's the real lesson of the oxygen desert. It's not just a relic of Earth's past, it's a warning. Atmospheres aren't permanent. They're delicate, dynamic things, balanced on a knife's edge between stability and collapse. One wrong turn, a runaway greenhouse effect, a failure of biological innovation, and a world can tip from habitable to hostile in geological moments. Yet even here, in this air-starved wasteland, there's a glimmer of hope. Recent observations hint at trace amounts of oxygen in the planet's upper atmosphere, possibly created by ultraviolet light breaking apart water vapor. It's not enough to breathe, not enough to sustain life as we know it, but it's a whisper of what could have been. And that's the haunting beauty of this place. It shows us how close Earth came to being a desert, how narrowly we avoided a fate where no lungs would ever fill with air. Every gust of wind on our own planet is a gift, a testament to the improbable alchemy of biology and geology. The oxygen desert stands as a silent sentinel, reminding us the line between a living world and a dead one is thinner than we dare to think. Imagine a world where you could walk from what feels like the North Pole to the South Pole without ever dipping your toes in an ocean. This is the Supercontinent Echo, a planet so vast yet so unified that its entire landmass is stitched together into one colossal continent, stretching from horizon to horizon without interruption. Its mountain ranges run like colossal spines across the surface, and its interior is a sprawling desert so immense it makes the Sahara look like a sandbox. But here's the eerie part: this isn't just a random quirk of geology. It's a mirror thrown back in time, reflecting Earth's own distant past, when all our familiar continents were fused together into the supercontinent Pangaea 250 million years ago. What makes the Supercontinent Echo so fascinating isn't just its size, but the way it breathes. Unlike Earth today, where oceans moderate temperatures and create diverse climates, this planet's weather is extreme and unforgiving. Its heart is a scorching wasteland where temperatures swing wildly between day and night. Meanwhile, the coasts are battered by relentless monsoons, the kind of storms that would rewrite entire landscapes in a single season. Scientists believe this is exactly how Earth's own supercontinental periods played out: massive inland deserts, violent coastal weather, and ecosystems forced to adapt or perish. But the real treasure lies beneath the surface. This planet's crust is riddled with scars, fault lines where the land is slowly, inevitably tearing itself apart. Sound familiar? It should. These are the same forces that once shattered Pangaea, sending continents adrift like broken puzzle pieces. Watching the supercontinent Echo is like having a front-row seat to Earth's own tectonic drama, but in fast forward. Some researchers even think they've spotted the beginnings of a new ocean basin, a place where the crust is thinning and magma is rising. The first whispers of a future where this monolithic land fractures into something new. And that's where the haunting question comes in. If this planet is following Earth's past, could it also preview our future? Geologists predict that in another 250 million years, Earth's continents will collide once again, forming a new supercontinent nicknamed Pangaea Proxima. By studying the supercontinent Echo, we might catch a glimpse of what that world will look like, how its weather will rage, where its deserts will form, even how life might cling on in the face of such radical change. There's a deeper lesson here, too. Supercontinents aren't just geological curiosities, they're planetary turning points. When land masses merge, climates shift, oceans reorganize, and evolution gets a shake-up. The rise of Pangaea may have triggered Earth's greatest mass extinction. Could the same happen to the supercontinent Echo? And if so, does that mean our own distant descendants are destined for another apocalypse of fire and upheaval? For now, this distant world remains a silent oracle, its cracked surface holding secrets we're only beginning to decipher. But one thing is certain, it's a reminder that the ground beneath our feet isn't as solid as it seems. Continents move, climates transform, and Earth, just like its cosmic twin, is always in flux, a story written not in stone, but in shifting, restless rock. The Methane Swamp doesn't just defy expectations, it shatters them. Picture a world where the air isn't thin or toxic, but thick, a soupy haze of methane and organic compounds that cling to the landscape like a perpetual fog. Sunlight barely penetrates this murky shroud, casting everything in an eerie, twilight glow. Rivers of liquid methane carve valleys into the surface, while vast wetlands of hydrocarbon sludge bubble with gases that would be lethal to Earth's lifeforms. At first glance, this seems like a dead end for biology, until you remember that Earth once looked just as hostile. Its early atmosphere choked with methane long before oxygen became the breath of life. What makes the Methane Swamp so revolutionary isn't just its composition, but the possibility it forces us to confront. Life doesn't need oxygen to thrive. On Earth, we're so accustomed to thinking of oxygen as the cornerstone of biology that the idea of methane-based life feels alien, literally. But this planet's chemistry is a playground for radical alternatives. Scientists have detected complex organic molecules swirling in its atmosphere, chains of carbon and hydrogen that could serve as the building blocks for organisms with a completely different biochemical blueprint. Imagine microbes that breathe methane instead of oxygen, or creatures whose cells use liquid hydrocarbons the way ours use water. the most tantalizing clue. Seasonal changes in the planet's atmospheric methane levels, fluctuations that can't be explained by geology alone. Some researchers speculate these shifts could hint at biological activity, methane-consuming or methane-producing lifeforms cycling gases through their ecosystem. It's a long shot, but not impossible. After all, Earth has its own methane-loving extremophiles, like the archaea lurking in deep-sea vents or Arctic permafrost. If life can flourish in those niches, why not in a world built for it? Here's where the methane swamp turns our assumptions upside down. For decades, the hunt for habitable planets fixated on Goldilocks zones, regions where liquid water could exist. But this world orbits far outside that zone, its surface far too cold for water oceans. Instead, it has methane oceans, and that changes everything. It suggests habitable zones might be broader, weirder, and more diverse than we ever imagined. A planet doesn't need to mimic Earth to harbor life. It just needs the right chemistry and energy, and that's the haunting beauty of this place. It's not just a relic of Earth's past. It's a window into a parallel evolutionary path, a universe where life took a left turn instead of a right. If organisms do exist here, they'd be so fundamentally different, we might not even recognize them as alive at first glance. Their metabolism, their reproduction, their very cells, all would be built on rules we're only beginning to decipher. So the next time you take a breath of Earth's sweet, oxygen-rich air, remember, it's just one recipe for life. The methane swamp whispers of others, of possibilities unbound by our planet's history. And in that whisper lies a humbling truth. The universe, in all its creativity, might have written the story of life in languages we've yet to learn. Step onto the Tidal-Locked Relic, and you'd feel like you're straddling the edge of reality itself. One side of this planet bakes under the relentless glare of its star, a scorched wasteland where temperatures soar high enough to melt lead. Turn your head, and you're met with an endless night, a frozen hemisphere where the cold is so absolute, even the air has turned to snow. Between them lies the only place where life might cling, a narrow band of twilight, where the star forever hovers at the horizon, casting long shadows across a world divided. But here's the twist: this isn't just a freak of celestial mechanics. It's a mirror to Earth's own infancy when our planet spun so slowly. A single day could last weeks or even months. The secret to this world's eerie duality lies in its orbit. Gravitational forces have locked it to its star, much like our moon is locked to Earth, ensuring one side always faces the light while the other drowns in darkness. Scientists call this tidal locking, and while it might seem like a death sentence for life, the tidal-locked relic tells a more nuanced story. Its twilight belt, where day meets night, could be a haven, a place where temperatures hover in a delicate balance. Rivers might flow from the molten day side, carving paths through the twilight before freezing solid in the endless night. Storms, fueled by the extreme temperature contrast, could rage along the boundary, redistributing heat and chemicals in ways that mimic Earth's own early weather systems. But the real fascination isn't just the planet's present, it's what it reveals about Earth's past. Billions of years ago, before the moon's gravitational pull stabilized our rotation, Earth's days were likely just as sluggish. Some models suggest a single rotation could have taken over 100 hours, meaning sunrise to sunrise would feel like an eternity. That slow spin would have created climate extremes not unlike the tidal-locked relics, with blistering days and frigid nights. Yet life emerged anyway, adapting to the harsh rhythms of a world caught between fire and ice. That's why this distant world captivates astrobiologists. If life exists in its twilight belt, it wouldn't look like anything we're familiar with. Plants might orient themselves to the forever horizon sun, their leaves tracking its faint light like solar panels. Animals could evolve to migrate between the day and night edges, following temperature gradients like Earth's birds follow seasons. Even more intriguing are the subsurface possibilities. Beneath the frozen night side, geothermal heat could sustain liquid water pockets, dark, isolated ecosystems akin to Earth's deep sea vents, where life thrives without sunlight. The Tidal-Locked Relic challenges our very definition of habitable. We're used to thinking of life as needing a steady cycle of day and night, but this planet whispers a different truth. Life is stubborn, creative, and relentless. It finds a way in the cracks, in the margins, in the places where logic says it shouldn't exist. And that's the profound lesson here. Earth's history wasn't a smooth march toward comfort. It was a series of brutal extremes, each one a crucible that forged resilience. This distant world, with its eternal dawn and unyielding dark, is a reminder that life doesn't need perfection, just a chance. And sometimes the most unlikely places hold the keys to our own origins. The Dust Bowl planet doesn't just have storms, it is a storm. Imagine a world where the sky is never blue, where the horizon disappears behind a perpetual haze of swirling dust, and where the very ground beneath your feet is constantly shifting, carried away by winds that never cease. This isn't a temporary disaster or a seasonal phenomenon. It's a permanent state, a planet-wide desertification so extreme, it makes the Sahara seem like an oasis. But here's the chilling part. This isn't just a distant oddity. It's a haunting reflection of Earth's own Dust Bowl era, that devastating period in the 1930s when overplowing and drought turned fertile American farmlands into barren wastelands. Only here, the catastrophe has engulfed an entire world. What makes this planet so unsettling isn't just its brutality, but its origins. Scientists believe it wasn't always this way. Scans reveal ancient river valleys fossilized beneath the dust, proof that water once flowed here. So what went wrong? The answer lies in a cascade of feedback loops, processes where small changes trigger bigger ones, spiraling out of control. On Earth, we saw a glimpse of this during the Dust Bowl. Poor farming practices stripped the land of protective grasses, leaving soil exposed. When drought hit, the winds carried that soil away, creating storms that darkened skies for years. The Dust Bowl planet took that tragedy and magnified it 1,000-fold. Its stars, slightly hotter and brighter than our sun, evaporated its oceans faster. Without water to regulate temperatures, the climate swung wildly, killing off vegetation that once anchored the soil. Then, as the dust storms grew, they blocked sunlight, cooling the planet just enough to prevent rain from ever returning. A self-reinforcing cycle of ruin. Parallels to Earth's current climate struggles are impossible to ignore. While we're not at risk of a global dust bowl yet, the mechanisms are eerily similar. Deforestation, overgrazing, and rising temperatures are already causing deserts to expand at alarming rates. Places like the Sahel in Africa or the American Southwest watch helplessly as fertile land turns to dust decade by decade. The Dust Bowl planet is a stark reminder. Desertification isn't just about losing farmland, it's about tipping points. Once certain thresholds are crossed, the damage becomes irreversible, and the storms take on a life of their own. Yet amid the bleakness, there's a sliver of hope. This planet's tragedy is also a laboratory. By studying its atmospheric chemistry, scientists are learning how to predict and potentially prevent similar feedback loops on Earth. Some even speculate about regreening technologies tested in places like China's lowest plateau, where careful restoration has revived dead land. Could those methods one day be scaled to a planetary level? The Dust Bowl planet doesn't answer that question, but it does something more valuable. It forces us to ask it, and that's the real lesson here. This world isn't just a cautionary tale. it's a mirror held up to our own choices. Every decision about land use, every policy on emissions, every innovation in conservation, they're all threads in a larger story, one that could lead to renewal or ruin. The dust storms of that distant world are silent, but their message echoes loud and clear. Climates don't collapse overnight. They're eroded grain by grain until one day the wind carries everything away. The question isn't whether Earth could become a dust bowl. It's whether we'll heed the warning before the storm arrives. The deep freeze is a world where the very air has turned to snow. Not metaphorically, literally, this planet's atmosphere has frozen solid, collapsing into layers of nitrogen and oxygen ice that blanket the surface like a funeral shroud. Temperatures here dip so low, they make Antarctica feel like a tropical getaway, with thermometers hovering just a few degrees above absolute zero. It's a place so hostile, even time seems to slow, as if the cold has leached the energy from the very fabric of reality. Yet hidden in this icy tomb might lie clues to one of Earth's most enigmatic chapters, the snowball Earth periods, when our own planet froze from pole to pole, not once, but multiple times over hundreds of millions of years. What makes the deep freeze so mesmerizing isn't just its brutality, but its contradictions. At first glance, it seems like the ultimate dead end for life, a world where even the air has given up. But look closer and you'll find tantalizing anomalies. Thermal scans reveal pockets of geothermal heat seeping through the ice, creating subterranean oases where liquid water might still persist. These hidden caverns, warmed by the planet's own radioactive decay, could be sanctuaries for life unlike anything we've ever seen. Imagine microbes that don't just endure the cold, but thrive in it, their biochemistry rewritten to function at temperatures that would shatter earthly cells. This isn't science fiction. On our own planet, we've found extremophiles flourishing in places once deemed uninhabitable, bacteria buried in Antarctic ice, fungi growing inside nuclear reactors, even organisms that reverse their metabolism to survive deep freezes. If life can cling to those razor-thin margins on Earth, why not in the deep freeze underground labyrinths? Some researchers speculate these icy vaults might harbor ecosystems built around chemosynthesis, where microbes derive energy not from sunlight, but from chemical reactions between rock and water. It's a haunting parallel to Earth's own snowball periods, when life may have survived in similar refuges, waiting for the thaw. But here's the spine-tingling twist. The deep freeze might not always have been this way. Orbital data suggests this world once had a thicker atmosphere and milder temperatures until something tipped it over the edge. Maybe its star dimmed, or a catastrophic release of frozen gases triggered a runaway cooling effect. Sound familiar? Earth's own snowball episodes likely began with similar triggers, like volcanic eruptions spewing sunlight-blocking ash or the weathering of rocks pulling carbon dioxide from the air. The difference: Earth eventually rebounded, its volcanoes belching enough greenhouse gases to melt the ice and reset the climate. The deep freeze, it seems, never got that second chance. That's what makes this world so profound. It's not just a relic of Earth's past, it's a glimpse of what could have been if our planet's climate roller coaster had stalled at the bottom. Every ice sheet, every frozen gas deposit, every whisper of geothermal heat is a puzzle piece in understanding how worlds live, die, and sometimes cheat death. And if against all odds life does exist there, it would rewrite the rules of biology, proving that even in the universe's coldest corners, the spark of life finds a way to flicker. So the next time you shiver on a winter morning, remember, Earth's coldest days were far worse, and yet here we are. The deep freeze stands as a silent testament to resilience, a reminder that life's tenacity is matched only by the universe's creativity. And who knows, maybe somewhere beneath those endless ice sheets, in the dark and the cold, something is waiting to teach us just how far that tenacity can go. The carbon copy doesn't just resemble Earth's past. It feels like stepping into a time machine set to the age of the dinosaurs. This world's atmosphere is a thick, soupy haze of carbon dioxide, trapping heat so efficiently that its surface temperatures could melt lead. Oceans, if they ever existed, have long since boiled away, leaving behind vast salt flats and cracked riverbeds as monuments to a wetter era. Yet despite its hellish appearance, this planet holds a mirror to one of Earth's most transformative periods, the Mesozoic, when CO2 levels were 5 times higher than today, and lush jungles stretched from pole to pole. What makes the carbon copy so unsettling isn't just its heat, but how familiar its story feels. Scientists believe this world started out much like Earth, temperate, with liquid water and a stable climate. But somewhere along the way, it crossed a threshold. Maybe volcanic eruptions pumped too much CO2 into the air. Perhaps its oceans stopped absorbing carbon, or its plants died off in a mass extinction. Whatever the trigger, the result was a runaway greenhouse effect, a feedback loop where rising temperatures released even more CO2 from rocks and seas, which trapped more heat, which released more gas, on and on until the planet became a furnace. Here's where the parallels get unnerving. Earth flirted with this fate 56 million years ago during the Paleocene-Eocene thermal maximum, when a sudden CO2 spike sent global temperatures soaring. Crocodiles swam in the Arctic and rainforests grew in Wyoming. But that event was a blip compared to the carbon copy's eternity of heat. This planet shows us what happens when the emergency brake fails, when warming isn't a temporary crisis but a permanent state. Yet within this cautionary tale lies a glimmer of hope. By studying the carbon copy's atmospheric chemistry, climatologists are piecing together how greenhouse gases interact over geological timescales. They've spotted curious anomalies, minerals that only form in certain CO2 concentrations, isotopic signatures hinting at ancient rainfall patterns, clues that could refine Earth's own climate models. Some even speculate about reverse engineering this world's history to identify early warning signs our planet might be approaching a tipping point. The most haunting question isn't whether Earth could become a carbon copy, it's how close we've already come. In just 2 centuries, we've raised atmospheric CO2 levels faster than any natural event in 66 million years. While we're still far from Mesozoic concentrations, the trajectory echoes this doomed world's early days. That's why scientists call it both a warning and a wake-up call. Unlike the carbon copy, we still have time to rewrite the ending, to swap a runaway greenhouse for a stabilized climate. But the clock is ticking, and this distant world, with its silent deserts and fossilized rivers, stands as a cosmic reminder. Planetary balances are fragile, and once they shatter, there's no going back. The water world doesn't just have oceans, it is an ocean, a planet where land is nothing more than an afterthought. Imagine sailing across endless waves day after day, with nothing but the occasional jagged peak breaking the horizon like the spine of some drowned giant. This isn't a world of beaches or coastlines. It's a liquid realm where storms roll uninterrupted for thousands of miles and tides swell with no continents to tame them. Yet beneath its alien surface lies a mirror to Earth's own infancy, a time when our planet's crust was still cooling and the first landmasses were little more than volcanic specks in a global sea. What makes this world so mesmerizing isn't just its vastness, but its simplicity. Without continents to divert currents or mountains to disrupt weather patterns, its oceans operate on a scale we can barely comprehend. Cyclones here aren't just storms, they're planetary events, swirling for years without ever hitting land. tidal forces, unimpeded by shallow shelves, create waves that could swallow cities whole. Even the water itself is different, laced with minerals leached from a seafloor that's never been exposed to air. It's like staring into Earth's Archean eon, 4 billion years ago, when the first scraps of land were still struggling to rise above the waves. But here's where the mystery deepens. Scans of the water world's seafloor reveal something astonishing. Massive underwater plateaus, not quite islands, but not quite abyssal plains either. These could be the precursors to continents, the first stirrings of a geological process that, given time, might push land above the surface. That's why scientists are obsessed with this place. It's a snapshot of Earth's tectonic adolescence, a time when the machinery of plate tectonics was just gearing up, heaving rock upward in fits and starts. The real question isn't just how this world mirrors Earth's past, it's whether it hints at our future. Some models suggest that as Earth's tectonic activity slows over billions of years, our continents might erode or sink, leaving behind a planet not unlike this one. Could the water world be a preview of that distant era, when the last mountains crumble into the sea and the oceans reclaim everything? Or is it frozen in an earlier phase, destined to one day sprout landmasses of its own? There's another tantalizing possibility lurking in those endless waters: life. Earth's own oceans were the cradle of biology, and the chemistry of the water world, rich in hydrothermal vents and organic molecules, checks all the boxes for habitability. But what kind of life could exist in a world without shores? Without estuaries or tidal pools, evolution would have to take a different path. Picture ecosystems built around floating mats of algae, or creatures that migrate vertically through water columns instead of crossing landscapes. Even intelligence, if it arose here, would be utterly alien, shaped by currents and pressure, not trees or savannas. That's the haunting beauty of this world. It challenges our Earth-centric assumptions at every turn. Land isn't just scarce, it's irrelevant. Weather isn't moderated by geography, it's raw and unfiltered. Life, if it exists, would be untethered from the rhythms of day and night, seasons or soil. And yet, for all its strangeness, the water world feels eerily familiar, a reminder that Earth, too, was once a blue marble with no one to admire its shores. Every wave that crashes against its lonely rocks is a whisper from our own deep past, a time when the stage was set for continents to rise, but the play had barely begun. So the next time you stand on a beach watching the tide roll in, remember, this is the exception, not the rule. Most worlds, it seems, belong to the ocean. And in their depths, they hold the secrets of how ours learned to stand above them. The Iron Planet is a world where the ground itself bleeds rust. Vast plains of oxidized iron stretch to the horizon in every direction, their reddish-brown hues painting the landscape like a colossal, forgotten forge. Towering cliffs reveal banded stripes of iron-rich rock alternating with silica, a geological record written in rust. At first glance, it seems like the aftermath of some cosmic catastrophe, a planet scoured by fire and left to corrode. But this metallic wasteland is actually one of the universe's most profound time capsules, a near-perfect mirror of Earth's own adolescence 2.5 billion years ago, when our planet's rocks turned red and its atmosphere filled with oxygen for the very first time. What makes this world so extraordinary isn't just its appearance, but the story etched into its crust. Those banded iron formations aren't random. They're pages from a planetary diary chronicling the most dramatic chemical revolution in Earth's history. On our own planet, similar layers formed when ancient microbes began exhaling oxygen as waste, a byproduct of their newfound ability to harness sunlight through photosynthesis. That oxygen, once rare, reacted violently with the iron dissolved in Earth's oceans, rusting it out of the water and depositing it on the seafloor in rhythmic stripes. The iron planet's surface suggests an identical drama unfolding in slow motion, its own rusted bands hinting at a biological upheaval frozen in time. But here's where the plot thickens. Unlike Earth, where this process eventually led to an oxygen-rich atmosphere, the iron planet seems stuck in transition. Its air remains thin and mostly nitrogen, with only trace amounts of free oxygen. So what stalled the process? The answer might lie in the planet's unusual magnetic field, or lack thereof. Without a strong magnetosphere to shield its surface from solar wind, any oxygen produced by potential microbes could be stripped away into space before it accumulates. That would leave the planet permanently trapped between two eras, a world that started the journey toward oxygenation but never reached the destination. The implications are staggering. If life exists here, it might be caught in an evolutionary limbo, organisms that invented photosynthesis but never reaped its full rewards. Scientists speculate they could resemble Earth's earliest cyanobacteria, clinging to shallow pools or hydrothermal vents, their oxygen byproduct instantly binding with iron or vanishing into the void. There's even evidence of iron breathers in the planet's deeper layers, microbes that might metabolize rust itself, just as some earthly bacteria do in abandoned mines and cave systems. This world's true gift, though, isn't just a window into Earth's past. It's a laboratory for understanding how common or rare our oxygen-rich atmosphere might be in the cosmos. For every planet like Earth that successfully transitioned to a breathable sky, how many others got stuck like the iron planet, their biological revolutions unfinished? The answer could reshape our search for life elsewhere, shifting focus from worlds that mirror our present to those frozen in pivotal moments. Standing on those rusted plains, you'd feel the weight of cosmic irony. The very element that makes this planet seem dead, its iron-rich crust, is actually the signature of a process that gave Earth its life-sustaining air. Every band, every layer, every flake of rust is a testament to the universe's slow alchemy, the way chemistry and biology dance together to transform worlds. And buried in that metallic silence might be the most humbling lesson of all. Our blue sky wasn't inevitable. It was a fragile victory, won by countless generations of microbes we'll never know. The iron planet shows us what could have been, and how narrowly we escaped becoming a world where oxygen is just another mineral in the ground. The storm giant doesn't just have weather, it is weather. Imagine a planet where the sky never calms, where hurricanes wider than entire continents spiral across the surface like immortal beasts, their howling winds tearing at the landscape for centuries without pause. These aren't temporary disturbances, they're permanent fixtures, storms so vast and enduring, they've etched their paths into the planet's crust like scars. At first glance, this seems like the universe's most chaotic fluke until you realize it's a distorted mirror to Earth's own past, when our atmosphere was younger, hotter, and far more violent. What makes this world so terrifyingly fascinating isn't just the scale of its storms, but what fuels them. Unlike Earth, where hurricanes dissipate after hitting land or crossing cold water, the storm giant has no such relief. Its oceans are uniformly warm, its continents flat and scattered, offering nothing to break the cycle. Heat from its star pours into the seas, evaporating water vapor that feeds the tempests like kindling to a fire. Meanwhile, the planet's rapid rotation, spinning nearly twice as fast as Earth, whips these storms into monstrous, self-sustaining systems. The result is a meteorological nightmare, a world where the concept of clear skies doesn't exist. Yet hidden in this chaos is a clue to one of Earth's most enigmatic periods, the Paleoproterozoic, 2.5 billion years ago. Back then, our planet's atmosphere was thicker, hotter, and richer in greenhouse gases. Some scientists believe superstorms raged across the young Earth, fueled by temperature extremes we can barely imagine. The storm giant lets us test those theories in real time. By studying its atmospheric dynamics, researchers have uncovered something startling. These endless hurricanes aren't random. They're part of a planet-wide heat distribution system, a violent but effective way to balance temperatures between equator and poles. That revelation turns our assumptions upside down. We think of storms as destructive outliers, but on this world, they're the glue holding the climate together. Without them, the equator would boil while the poles froze solid. It's a sobering reminder that extreme is relative. What seems apocalyptic to us might be another planet's version of stability. And that raises the haunting question, could Earth ever face storms like these? The answer lies in the delicate balance of our own climate. While we'll never match the storm giant's fury, rising global temperatures are creating stronger, slower-moving hurricanes. Warm ocean waters, like those fueling this alien world's tempests, already intensify storms like Katrina and Maria. Some models even suggest future hurricanes could last weeks instead of days, their paths growing erratic as atmospheric currents shift. The storm giant isn't just a spectacle, it's a stress test, showing us what happens when a climate tips past the point of no return. But here's the twist. Amid all this violence, the storm giant might harbor life. Not in the open, of course, nothing could survive those winds, but deep in the ocean, where thermal vents could nurture ecosystems untouched by the chaos above. It's a reminder that life finds a way, even in the most hostile corners of the cosmos. And if that's true, then this world's endless storms aren't just a warning. They're proof that resilience wears many faces, and that even in the universe's most furious tempests, the seeds of survival might be waiting. So the next time you watch a hurricane spin on a weather map, remember, that storm is a whisper compared to the screams of the storm giant. And in its fury lies a lesson not just about the past, but about the fragile equilibrium that keeps our own skies, for now, mercifully quiet. The Twilight World hangs in the cosmos like a half-remembered dream, bathed in an eternal dusk that never brightens into day nor fades into true night. Its dim red star casts a weak crimson glow across the surface, painting everything in hues of rust and shadow. Trees here, if they exist, wouldn't know the concept of sunrise, their leaves forever straining to catch photons from a sun that feels more like a distant ember. Yet this hauntingly beautiful world isn't just a cosmic oddity. It's a living museum, preserving conditions eerily similar to Earth's earliest days, when our own young sun burned 30% fainter than it does today. Scientists call this the faint young sun paradox, the mystery of how Earth remained warm enough for liquid water despite receiving so little sunlight. The Twilight World offers a chance to study that puzzle firsthand. Its surface temperatures hover in a precarious balance, warmed not by starlight but by a thick atmosphere rich in greenhouse gases like methane and carbon dioxide. Sound familiar? That's likely the same cocktail that kept Earth from freezing over 4 billion years ago. But here's where the parallels twist. While Earth eventually developed oxygen-producing life that transformed its skies, the Twilight World remains frozen in time, its atmosphere a relic of that primordial era. What does that mean for life? The rules are rewritten under such dim light. Traditional photosynthesis, with its reliance on abundant sunlight, would struggle here. But nature is inventive. Some researchers speculate about organisms that harness infrared radiation instead of visible light, or microbes that combine faint starlight with chemical energy from hydrothermal vents. There's even evidence of bizarre shadow ecosystems in the planet's twilight zone, where organisms might exploit fleeting gradients of light and dark, like Earth's deep-sea creatures navigating by bioluminescence. The most tantalizing clue lies beneath the surface. Thermal scans reveal vast networks of subsurface caves warmed by geothermal heat, their walls glistening with a strange, slime-like substance that defies initial analysis. Could this be the Twilight World's answer to algae, a life form that thrives not by reaching for the sun, but by embracing the dark? If so, it would rewrite our understanding of photosynthesis, proving that light doesn't need to be bright, just constant. This world's true lesson isn't just about the past, it's about possibility. Around dim red dwarfs, which make up 75% of stars in our galaxy, planets like this could be the rule rather than the exception. If life can find a way here in this eternal dusk, then the universe might be far more crowded than we ever imagined, and that changes everything. The Twilight World whispers a radical idea. Maybe we've been looking for life in the wrong light all along. The salt flat stretches before you like a frozen wave, an endless expanse of blinding white where the ground cracks into geometric patterns under a relentless sun. This isn't just a desert, it's a planetary-scale relic, a world where oceans once surged but now exist only as ghosts trapped in crystalline prisons. Every inch of its surface glitters with salt crust so thick they've buried mountains, leaving behind a topography of jagged ridges and glass-smooth plains. Yet beneath this sterile facade lies a mirror to Earth's own chaotic youth, when our planet's first oceans alternated between flooding continents and evaporating into vast salt pans under a blistering primordial sun. What makes this world so eerily compelling isn't just its emptiness, but the paradox it represents. Salt, for all its harshness, is a silent architect of life. On Earth, the same evaporative basins that created Death Valley or the Bonneville salt flats also concentrated the minerals and organic molecules that allowed early life to assemble. The salt flats' endless plains might seem lifeless, but their chemistry tells a different story, one where hypersaline pools act as cosmic petri dishes, forcing dissolved compounds into close proximity. Scientists have detected amino acids and lipids trapped in this planet's salt crystals, complex molecules that on Earth served as the raw materials for life's first experiments. The real mystery lies in the planet's subterranean veins. Beneath the salt crust, probes have mapped labyrinthine channels of briny groundwater, liquids so saturated with salts they remain liquid even in sub-zero temperatures. These aren't just relics of a lost ocean, they're dynamic systems, circulating minerals and heat in ways that mimic Earth's hydrothermal vents. Some researchers speculate these hidden currents could host extremophiles akin to Earth's halophiles, organisms that don't just tolerate salt, but demand it. Their cells evolved to harness the very conditions that would kill most life forms. Here's where the salt flat turns from a curiosity into a revelation. Earth's own evolutionary history might have hinged on similar briny crucibles. When the first cells struggled to stabilize their membranes against osmotic chaos, salt flats could have provided the perfect training ground and environments where only the most resilient chemistries survived. This world's endless wastes might be showing us the harsh filter through which life on Earth first crawled. A trial by salinity that separated fleeting chemical reactions from self-sustaining biology. Yet the haunting question remains, if life exists here, how would we even recognize it? In a world without liquid water as we know it, organisms might rely on brine channels or salt-stabilized gels to shuttle nutrients. Their metabolisms could exploit crystalline structures to organize reactions, turning the salt itself into a scaffold for complexity. It's a radical vision, one where life isn't just surviving in salt, but using it as a tool, rewriting the rules of biochemistry in the process. The salt flat's true gift isn't just a window to Earth's past. It's a challenge to our very definition of habitable. For decades, we've searched for worlds with Earth-like oceans, but this planet whispers a subversive truth. Sometimes, the most promising cradles for life aren't blue with water, but white with salt. Every crack in its surface, every shimmering crystal, is a reminder that life's origins might be messier, stranger, and more chemically daring than we ever imagined. And buried in those briny depths could be the answer to one of science's oldest questions, not just how life began, but how close it came to never beginning at all. The lava moon hangs in orbit around its gas giant like a jewel forged in fire, its surface a living canvas of molten rock and shifting plains. Tidal forces from the massive planet below stretch and knead this world like cosmic dough, generating enough internal heat to keep its core churning and its crust in a state of perpetual rebirth. Rivers of lava wider than the Amazon carve fresh channels across the landscape, while volcanic plumes paint the thin atmosphere with swirling ash. At first glance, it seems like a vision of hell, until you realize you're staring into Earth's own fiery infancy, a time when our planet's surface was just as restless and raw. This isn't just another volcanic world. What sets the lava moon apart is its rhythm, the way its eruptions pulse in time with the gravitational tug of war between moon and planet. Every orbit brings new quakes, new fissures, new fountains of magma erupting in synchrony with the tides. It's a dance of destruction and creation, where landscapes are rewritten in days rather than millennia. Scientists believe Earth's early days played out similarly, when the moon was closer and its tidal pull far stronger, stirring our planet's mantle into a frenzy of activity. The difference: Earth's fires eventually cooled, its crust thickening into stability. The lava moon, trapped in its gravitational embrace, never got that chance. Yet within this chaos lies a revelation about how planets grow up. By studying the moon's lava composition, researchers have spotted something extraordinary: minerals that only form under extreme pressure, hinting at a subsurface ocean of magma much deeper than Earth's ever was. This could be the key to understanding why some worlds, like ours, develop rigid tectonic plates while others remain molten playgrounds. The lava moon's unrest isn't random, it's a laboratory for the forces that shaped every rocky planet in the cosmos. The most haunting parallel isn't just geological, it's biological. Earth's most ancient life forms likely emerged in similar infernos, around hydrothermal vents where mineral-rich fluids met scalding heat. Could the lava moon's tidal vents host their own experiments in chemistry? Its plumes contain organic molecules, and its lava tubes, shielded from radiation, might offer pockets of stability where complexity could arise. Life here wouldn't look like anything we know. It might thrive in the magma itself, feeding on sulfur and metal. But the possibility forces us to rethink life's limits and where we should search for it. What makes this world truly humbling is its impermanence. Unlike Earth's mountains, which stand for eons, the lava moon's peaks rise and collapse in cycles measured in years. Continents of cooled basalt drift across molten seas only to be swallowed anew. It's a reminder that planets aren't static monuments but living processes, always in flux. And somewhere in that endless cycle of melting and solidifying lies the answer to why Earth became what it is, and how narrowly we avoided becoming a world where the ground never stops shaking. Standing on the lava moon would feel like witnessing creation itself, a front-row seat to the universe's workshop. Every eruption, every tidal tremor is an echo of the forces that built our home. And as we watch this world remake itself in real time, we're left with a profound truth. The difference between a cradle for life and a perpetual forge isn't luck, it's timing. Earth's fires quieted just enough, The lava moons never did, and in that distinction lies the fragile miracle of our existence. The frozen jungle is a world where winter has sculpted madness into beauty, a planet where glaciers have sprouted into towering, intricate structures that resemble Earth's ancient forests, their branches not of wood but of ice. These aren't mere icicles, they're colossal spires, some stretching hundreds of meters high, their fractal patterns so precise they look designed. Sunlight filters through their translucent canopies, casting prismatic shadows across a landscape that feels both alien and hauntingly familiar. At first glance, it's easy to dismiss this place as a frozen wasteland. But look closer, and you'll realize you're standing in what might be the universe's most surreal ecosystem, one that challenges everything we thought we knew about the boundaries of life. What makes these ice trees so extraordinary isn't just their appearance, but how they form. Unlike Earth's forests, rooted in soil and fed by sunlight, these structures grow from a delicate dance of temperature, humidity, and subterranean geysers. Warm water, rich in minerals, erupts from deep below the frozen crust, meeting the planet's frigid surface air. The result is a slow-motion explosion of crystallization, where water freezes mid-air, building layer upon layer into sprawling, arborescent monuments. Some researchers compare the process to Earth's frost flowers and delicate ice formations that bloom on Arctic sea ice but scaled up to the size of redwoods. Here's where the mystery deepens. Scans of the frozen jungle reveal something unexpected. Liquid brine rivers flowing inside the ice trees, trapped within microscopic channels. These aren't static sculptures, they're dynamic systems with fluids circulating like sap in a tree. Even more astonishing, those brines contain complex organic molecules, amino acids, lipids, even strands of nucleic acids arranged in patterns that defy simple chemical explanations. Could this be the universe's version of photosynthesis, where chemistry harnesses the energy of freezing instead of sunlight? Some astrobiologists think so. They point to Earth's own ice-loving microbes, which thrive in glaciers and Antarctic lakes, as proof that life can exploit even the most brittle environments. But the real question isn't just whether life could exist here, it's whether these ice trees are life. Not in the traditional sense, perhaps, but as a form of self-organizing complexity that blurs the line between geology and biology. Imagine a world where evolution operates not on cells but on crystalline structures, where reproduction means a geyser seeding new ice spires with mineral templates, where metabolism is the slow absorption of chemicals from frozen flows. It's a radical idea, but one that forces us to reconsider the very definition of life. After all, Earth's own trees are just another kind of chemistry, their growth governed by physical laws. Why couldn't ice, given the right conditions, become just as inventive? The frozen jungle's most profound lesson might be about perspective. For centuries, we've assumed life requires liquid water, temperate climates, and organic chemistry. But this world whispers a different truth. Life is a process, not a recipe. It's the universe's stubborn insistence on creating order from chaos, whether through DNA or crystalline matrices. And if that's true, then forests might grow anywhere, not just in soil, but in ice, in methane, in the molten cracks of tidal moons. Every spire in this frozen jungle is a challenge, a dare to expand our imagination beyond the green and the warm, into the infinite possibilities of the cosmos. So the next time you walk through a forest, pause for a moment. Those trees around you are just one variation on a theme, a single stanza in a much grander poem. Somewhere out there, in the silent dark, another world is writing its own verse in ice. The mirror lake doesn't just reflect light, it reflects time itself. Imagine standing on the shore of an endless metallic sea, so still and polished it's impossible to tell where the land ends and the sky begins. Your own silhouette stretches across the liquid surface, warped only by the faintest ripples as chemical winds whisper over the expanse. But this isn't water. These lakes are a surreal cocktail of liquid metals and rare earth elements, a brew so dense it flows like syrup, capturing every detail of the alien sky in perfect, eerie replication. At first glance, it feels like a mirage until you realize you're staring into a mirror of Earth's own primordial past, when our planet's first oceans were laced with metals leached from a still cooling crust. What makes these metallic lakes so mesmerizing isn't just their shine, but their secrets. Beneath their mirror-like surfaces, chemical reactions unfold in slow motion, forging molecules that haven't existed on Earth in billions of years. Scientists have detected chains of sulfur-iron compounds swirling in the depths, structures so complex they resemble the precursors to enzymes found in modern cells. It's like stumbling upon a cosmic laboratory where the universe is quietly running experiments, the same experiments that might have led to life's first sparks on Earth. The real magic happens at the edges where the lakes meet the land. Here, mineral-rich tides deposit crystalline lattices along the shores, their geometric perfection defying natural chaos. Some researchers believe these formations could be the key to one of biology's oldest mysteries, how simple molecules transitioned into self-replicating systems. On Earth, similar metal-rich pools may have acted as natural catalysts, their surfaces providing the scaffolding for RNA-like molecules to assemble. The Mirror Lake shores offer a chance to test that theory in real time, watching as chemistry inches toward complexity under the pull of an alien sun. But the most tantalizing clue lies in the lake's seasonal shifts. Every few years, the planet's orbit brings it close enough to its star to warm the metallic seas, triggering eruptions of shimmering plumes from the depths. These aren't just geysers, they're conveyor belts, hauling buried compounds to the surface where ultraviolet light can energize them into new configurations. It's a cycle eerily reminiscent of Earth's hydrothermal vents, where heat and chemistry collide to create the building blocks of life, the difference. This world's reactions play out on a stage of liquid metal under a sky untouched by oxygen. That's the haunting question the Mirror Lake forces us to confront. What if life's ingredients aren't rare, just waiting for the right container? Earth had water, this world has metals. Could the same dance of chemistry unfold in both? The answer might rewrite our search for life elsewhere, proving that the universe's recipe book is far thicker than we imagined. Every ripple on those mirrored surfaces is a reminder the line between a dead world and a living one might be as thin as a reflection. The gravity well doesn't just pull on objects, it bends reality itself. This is a planet where stepping onto the surface would feel like wearing a mountain as a backpack, where even the air is so dense it presses down like liquid. Time here ticks slower, warped by the immense gravitational pull, making a single hour stretch longer than anywhere else in the cosmos. At first glance, it seems like a place where nothing could survive until you realize this crushing force might be the key to understanding how life on Earth first clawed its way out of our own planet's ancient, denser atmosphere. What makes this world so unnervingly fascinating isn't just the weight. It's the way gravity rewrites the rules of physics and biology. Trees, if they exist here, wouldn't grow tall. They'd sprawl low and wide, their trunks reinforced with structures akin to steel cables. Animals would likely be compact, their bones thicker than concrete, their muscles optimized for efficiency over speed. Even the simplest organisms would face a relentless challenge: how to move, breathe, or reproduce under a force that makes every action feel like wading through molten lead. Yet hidden in this extreme environment are clues to Earth's own past. Billions of years ago, our planet's atmosphere was far denser, a soupy mix of gases that pressed down with nearly twice today's pressure. Early life forms evolved under these conditions, their biochemistry fine-tuned to withstand the squeeze. The gravity well offers a chance to study that forgotten era in real time, a living laboratory where high pressure isn't an anomaly, it's the norm. The most startling revelation comes from the planet's oceans, if you can call them that. Here, water doesn't flow so much as ooze, its molecules packed so tightly by gravity that it behaves almost like a gel. Yet within these sluggish depths, scientists have detected complex chemistry chains of molecules that self-organize into structures eerily reminiscent of cell membranes. Some researchers theorize that high pressure could actually accelerate certain biochemical reactions, forcing atoms together in ways that lower gravity environments wouldn't. It's a radical idea that crushing gravity might not stifle life but catalyze it. That's the haunting question this world forces us to confront. We assume life needs Earth-like conditions to thrive, but the gravity well whispers a different truth, that biology is endlessly adaptable, shaped not by some universal ideal, but by the raw physics of its environment. If life exists here, it wouldn't just be surviving the pressure, it'd be exploiting it, using gravity as a tool to drive evolution down paths we can barely imagine. And that's the real gift of this place. It's not just a relic of Earth's past, it's a challenge to our future. As we search for life beyond our solar system, we've fixated on planets with Earth-like gravity. But the gravity well proves that life's potential is far broader, that even the most extreme forces might forge their own versions of biology. Every second that ticks slower on its surface is a reminder the universe doesn't play by our rules. It invents its own. The dying star's companion drifts through the cosmos like a ghost in the machine, a world suspended in the crimson glow of its fading sun. This isn't the warm, golden light we know. It's the dim, ruddy flicker of a star in its final act, a swollen red giant that has consumed its own future to keep shining. The planet's surface is a study in twilight extremes, one hemisphere locked in perpetual sunset, the other in an endless, starless night. Temperatures swing between scorching heat where the dying star's feeble rays still touch the ground and frigid darkness where glaciers of frozen gases creep across the landscape. Yet this haunting scene isn't just a cosmic curiosity, it's a preview of Earth's own destiny, 5 billion years from now, when our sun exhausts its fuel and begins its slow, violent transformation. What makes this world so unsettlingly profound isn't just its bleak beauty, but the lessons etched into its crumbling geology. Scans reveal continents cracked by millennia of gravitational stress, their once mighty mountains ground down by relentless stellar winds. Rivers that once carved valleys now stand as empty canyons, their beds lined with minerals that only form under the slow bleed of evaporating water. Even the air is thinning, molecule by molecule, stripped away by the star's death throes. It's a world in retreat, a civilization of one where every feature whispers the same truth. Nothing lasts forever, but here's where the story twists. Amid the decay, there are whispers of resilience. Thermal imaging has detected pockets of liquid deep underground, shielded from the surface's extremes by layers of rock and ice. These hidden reservoirs could be the last refuges for any life that once flourished here, clinging to the fading warmth of the planet's core. It's a haunting parallel to theories about Earth's own far future, when microbial life might retreat to similar subterranean havens as our sun expands. The dying star's companion forces us to ask, when the light fades, does life surrender or simply adapt? The most chilling revelation, though, lies in the planet's orbit. Once comfortably nestled in the habitable zone, it's now being pushed outward as its star loses mass, a cosmic game of tug-of-war between gravity and momentum. This same dance will play out in our solar system, with Earth's orbit expanding even as the Sun's growing radius threatens to engulf it. The question isn't whether our planet will face this crisis, but how it will weather the storm. Will Earth, like its distant twin, become a barren relic, or will the ingenuity of whatever species calls it home by then find a way to cheat the cosmic clock? Standing on this world's surface, you'd witness time itself unraveling. The star that once nourished it now looms like an angry god, its swollen disk filling half the sky. Shadows stretch unnaturally long, and the very color of reality has shifted. No blues or greens remain, just endless variations of rust and amber. It's a funeral in slow motion, a planet mourning its own future. Yet even here, there's a strange kind of poetry. The dying star's companion reminds us that endings aren't just about loss, they're about transformation. Every atom in its soil, every gust of its thinning wind, is being recycled into the universe's next act, and that's the final, humbling lesson. Earth's fate is sealed not by human hands, but by the indifferent laws of physics. Yet in that inevitability lies a paradoxical freedom. If our world, like this one, is destined to become stardust again, then every moment we have, every forest, every ocean, every sunset is a temporary miracle. The dying star's companion doesn't just show us the future, it asks us to cherish the present, to live like we're the custodians of a flame that will one day flicker out. Because in the grand scale of cosmic time, even a planet's lifespan is just a heartbeat. These distant worlds aren't just alien landscapes, they're time machines. Each one holds up a mirror to Earth's past, reflecting chapters of our own story written in lava, ice, and atmospheric chemistry, but they're more than relics. They're teachers. The Methane Swamp challenges our assumptions about the ingredients for life. The Tidal-Locked Relic shows how biology might flourish in the unlikeliest places. The Gravity Well proves that even the most extreme environments could forge their own versions of existence. Together, they paint a humbling picture. Earth's history isn't unique. It's one variation in a grand cosmic symphony of planetary evolution. What's truly astonishing isn't just how these worlds resemble our past, it's how they expand our future. The storm giant warns of climate tipping points. The carbon copy lays bare the fragile balance of greenhouse gases. The dying star's companion whispers of endings we'll one day face. These aren't just scientific curiosities. They're glimpses into possible futures, roadmaps for where Earth might be headed if we ignore the lessons written in the stars. Yet amid the warnings, there's wonder. The frozen jungle's ice trees remind us that life could wear infinite forms. The Mirror Lake's metallic tides suggest new cradles for chemistry. Even the Dust Bowl planet, for all its desolation, hints at nature's relentless adaptability. These worlds don't just show us where we've been, they stretch our imagination for what's possible. So as we close this journey, here's the real takeaway. The universe doesn't repeat itself, but it rhymes. Every volcano, every glacier, every swirling storm on these distant worlds echoes Earth's own struggles and triumphs. They prove that planets, like lives, are shaped by chaos and resilience, by catastrophes and slow, patient change. And somewhere in that cosmic pattern lies our own story, not just as inhabitants of Earth, but as witnesses to a grander narrative written across the stars. Now it's your turn. Which of these worlds reshaped how you see our planet? Could the acidic mirror hold clues to life's origins? Does the Supercontinent Echo hint at Earth's next geological act? Drop your thoughts below, and if you've enjoyed this cosmic time travel, hit subscribe. The universe has countless more stories to tell, and we're just getting started. After all, every new telescope, every probe, every flicker of light from the void brings another piece of the puzzle. The past is out there, waiting in the dark. And so is the future.